Hi, my name is Emmanuel Aneke, and I spent my SNSP experience working under the Flatiron Institute. Namely, I worked for the Center for Computational Astrophysics, and under them, a plasma group known as the Plasmaniacs. My project was on particle-in-cell reconnection simulations for the affirmation of synchrotron-induced photon distribution changes. Now, that's quite the hefty name, but we will dissect it slowly. Now, question of the hour is, what is reconnection? First, we must understand what a pulsar is. The death of a star, a supernova, can leave behind different kinds of legacies, white dwarfs to neutron stars to black holes. But in an effort to save time, I won't get into the technicalities of what makes the results vary. Simply understand size does matter. To the left, you can see pictured the Crab Nebula, the result of a supernova that left behind a litter of gas and debris, the diametral size of about 9 quadrillion 500 trillion American football fields. And at its center lies a pulsar. So a pulsar is essentially this high energy, highly magnetized, highly dense star that spins and shoots out particles and radiation out of its magnetic poles. Just like how Earth has a north and south pole based on its magnetic field, most astronomical objects have their own poles as well. Reconnection is the name of the phenomenon that occurs when the magnetic field lines interact with the jets of high energy emitted particles. Now, the way I like to think of my project's overview is as a reassembly. See, I don't have a premium account to pulsars on demand, so I have to piece together whatever I can about the story from just the previews and trailers. What we see is limited to the radiation that is periodically shot at us. That's all that light is. We can deduce the energy of this light and the frequency at which it appears, and some other things, but that's it. From the light we see, previous researchers had come up with a couple of explanations for what's happening up there. One of those was reconnection. With the help of supercomputers, we can now simulate this reconnection process and attempt to bridge the gap between the light we see and what is happening. So far, reconnection seems to be right. It's the most logical explanation by far. The light we see tells us about the particle distribution, which in turn could tell us about the physical parameters of the pulsars, like its exact magnetic field strength. Crab and Vela are two real pulsars whose photon distribution data I analyzed. This is what is plotted to the right. Now, realistically, pulsars emit synchrotron radiation. This radiation causes particles to lose energy and cool. My assignment was to affirm our suspicions that changing this parameter called synchrotron radiation cooling would also correlate to the difference in appearances of the photon distributions of Crab and Vela pulsars. And if you look to the plot, you can see that the Vela has a slight increase in energy that maximizes and then falls off. However, Crab appears saturated and then merely falls off. To assist in the visualization of the pulsars, here are some images of global reconnection simulations. The global simply means that the entire pulsar is in view instead of a zoom perspective. On the right, you can see the aerial view of the pulsar where the jets of particles and radiation are resemblant to a hurricane. On the left, you can see perspective as if the jets are coming towards you. If you focus on the wiggly lines, this is where reconnection appears. Now it's time for the local simulations. What did I actually do? My simulations of reconnection involved a myriad of different parameters. An isolated two-dimensional box of plasma with opposing magnetic fields on either side was set to evolve over time with other elements at play. Pictured is the progression of the particle density over a few time steps. The lighter the shade, the higher the concentration of particles is. In the second panel, you can see pockets of dark spots and light spots. Those dark spots are called X points, and that's where the miscellaneous particles enter the center line, aka the current sheet, and the light spots are called plasmoids. Plasmoids are bubbles of concentrated plasma formed by circulating magnetic fields. Here is a progression of the energy density over time. As you can see, there is a direct correlation between the energy density and particle density. You can see that there are X points and plasmoids, respectively. Now you can see a progression of the magnitude of the magnetic field over time. There is another correlation between the magnitude of the magnetic field and the particle and energy densities. Now, to assist our endeavor of understanding reconnection, a magnetic field stream plot was layered over the particle density evolution. You can see the initial magnetic fields on either side of the current sheet are in opposing parallel directions. In the later time steps, you can see the absence of a magnetic field where there are X points and a circular magnetic field trapping particles sent from those X points into where there are plasmoids. Here's a movie of the plasma density over time while tracking a particle whose shade gets darker as it gains more energy. There we go, it appears on the bottom. Now, pictured are plots of the particle distribution for different reconnection simulations. The difference in each run is the gamma sin value, which is the rate of synchrotron radiation cooling. We can see the particle distributions decrease in domain as the gamma sin value approaches zero. But what does this mean as far as the light we see goes? Here in these plots, we see the particle distribution for certain gamma sin values averaged out, but to the right is the plot of the photon distributions, analogous to the respective gamma sin values. And if we look carefully, we can see something familiar. This is where it all comes full circle. The trends for the photon distribution of gamma sin equals 20 and gamma sin equals 200 look a lot like the photon distribution trends for the Crab and Vela pulsars, respectively. This affirms our theory that there is a definite and direct correlation between the rate of synchrotron radiation cooling and the shape of the photon distribution of pulsars from reconnection. Finally, I just want to thank everybody who participated and collaborated to make this program possible. Thank you, NSBP. Thank you, Simons Foundation. Special thanks to Casey for all the heavy lifting. And thank you to Heike, Bart, and Sasha for being an excellent group to work with. Thank you all for listening.